There are 4 variables that are manipulated in the different gas laws: pressure, temperature, volume, and moles. To see how one variable affects another, we have to hold the other 2 variables constant when we test them. First, we'll look at the relationship between pressure and volume. We'll hold moles and temperature constant by using a sealed container and a consistent temperature. When we decrease the volume, the pressure increases. This is an inverse relationship, which means the variables will be on the same side of the equation and the constant will be opposite. Here's the equation for pressure and volume. Pressure times volume equals some constant. Now, to see where Boyle's law is coming from, we need to look at the starting pressure and volumes, and finishing pressure and volumes. Mathematically, we can use substitution to put these 2 equations together, because they both equal the same value, K. In magic, we have Boyle's law. Let's try using it. A syringe is filled with air to 60 milliliters at 1 atmosphere. Then the syringe is sealed and compressed to 20 milliliters. What is the final pressure? Using Boyle's law, P1V1 equals P2V2, you can rearrange this equation now or after plugging in the numbers. It doesn't matter, but for neatness, I'm going to rearrange it now. I need the final pressure, or P2, so I'm going to get that isolated by dividing both sides by V2. Then clean it up and plug in the data. And you get 3 atmospheres. Do a concept check to see if that makes sense. Volume went down, pressure went up. That's inverse. Yep, it makes sense. The next law looks at pressure and temperature, keeping moles and volume constant, and sometimes it's called Gay-Lussac's law. We know that when temperature increases, pressure also increases. This is a direct relationship, which means the variables will be on opposite sides of the equation. Pressure equals temperature times the constant. Just rearrange a little, and now when we compare the before and after, we use substitution again to get Gay-Lussac's law. A flask filled with carbon dioxide is heated from 10 degrees Celsius to 40 degrees Celsius. The starting pressure is 98 kilopascals. What is the final pressure? We're using Gay-Lussac's law, and we need to find the final pressure, so let's rearrange the equation first. Just multiply both sides by T2, and you get a nice, clean equation. Fill in the data and calculate. But be careful. Use Kelvin instead of Celsius so that the mathematical proportions are accurate. And make sure that the final temperature is on top and the initial is on the bottom. And then you'll get 108 kilopascals, or, with correct sig figs, 110. Have you ever put a balloon in a freezer? Pull it out after a few hours and you'll find a shrunken balloon. As it warms up, it will come back to full size. As temperature goes down, volume goes down. This is a direct relationship. This is essentially the same as Gay-Lussac's law, except we're using volume instead of pressure. If you rearrange the equation and then substitute it, you get Charles's law. V1 over T1 equals V2 over T2. Here's a problem. A balloon is filled with 1.5 liters of air at 20 degrees Celsius, then placed in a freezer until it reaches a temperature of 5 degrees Celsius. What is the final volume? Well, let's rearrange Charles's law to find V2. Then we can plug in our data, after we convert Celsius to Kelvin, of course, and you get 1.4 liters, which makes sense because volume and temperature are directly related. Take a look at Boyle's law, Gay-Lussac's law, and Charles's law together. We can combine these 3 laws as long as we hold the number of moles constant. Amazing! Let's try a problem with this. 5.36 liters of nitrogen gas are at negative 25 degrees Celsius and 733 millimeters of mercury. What would be the volume at 128 degrees Celsius and 1.5 atmospheres? We are trying to find the final volume, so let's rearrange this equation to get V2 alone. We multiply both sides of the equation by T2 over P2, and when we clean this up, we get this pretty equation. Now we can just plug in our data, being sure to turn Celsius into Kelvin and to have the same types of pressure units. I chose to turn atmospheres into millimeters of mercury, but you could have gone the other way as well. Then you do your calculations, and you get the volume is 5.57 liters.
Ley de Avogadro. En condiciones normales de presión y temperatura, un mol de cualquier gas ideal ocupa un volumen de 22,4 litros. Esto es fundamental para comprender las variables que se mencionarán a continuación. El enunciado de la ley dice que el volumen de un gas es directamente proporcional a la cantidad del mismo. Esto significa que si aumentamos la cantidad de gas, aumentará el volumen del mismo. Si disminuimos la cantidad de gas, disminuirá el volumen del mismo. La expresión gráfica del enunciado es la siguiente. Esta ley relaciona la cantidad de gas en mol con su volumen en litros, considerando que la presión y la temperatura permanecen constantes. Por lo tanto, podemos expresar el volumen en términos matemáticos con la siguiente fórmula: B igual a K por N, que se traduce en que si dividimos el volumen de un gas por el número de moles que lo conforman, obtendremos un valor constante. Demostración. ¿Qué volumen ocuparán 3,5 mol de un gas en condiciones normales de presión y temperatura? 3,5 mol por 22,4 litros dividido en 1 mol es igual a 78,4 litros.
Y si las condiciones no son las normales, o bien no tenemos un mol, ¿cómo podemos relacionar las variables de un gas, es decir, su presión, su temperatura, su volumen, su número de moles, entre sí? O dicho de otra manera, conocidas 3 de estas variables, ¿cómo se puede conocer la cuarta? Esto se puede hacer porque cuando los gases se comportan idealmente, un gas se comporta siempre idealmente a presiones bajas y a temperaturas altas, las variables que definen el estado del gas, la presión, el volumen, el número de moles y la temperatura, se van a relacionar entre sí por la llamada ecuación de estado de los gases ideales. Esta ecuación de estado de los gases ideales es esta: P por V igual a N por R y por T. Vamos a ver qué significa cada una de estas variables que aparecen en la ecuación. Ahora bien, si yo hubiera puesto todo esto en las unidades del sistema internacional, es decir, en vez de presión en atmósferas en pascales, en vez de volumen en litros en metros cúbicos, la temperatura sí que está en Kelvin en el sistema internacional, si yo hubiera puesto estas unidades en el sistema internacional, presión en pascales, volumen en metros cúbicos, temperatura en Kelvin y número de moles en moles, R sería 8,314 julios partido mol Kelvin. Vamos a hacer un ejercicio para ver si lo hemos comprendido todo esto.